after starting with car data frame using the pipe operators. After grouping by manufacturer, we summarize by forming a new variable called sales 2018 sum, a variable calculated as the sum of sales in 2018. So we can find the result by viewing it in this editor. So each manufacturer, as before, takes a different role. And in this new column, sales 2018 sum, we have the summation of sales. All right, this is all the steps instructed here as the cumulative exercise. As you can see, up to here, there may not be substantial evidence showing that writing the script can be easier than using Excel functions. But if we move on to more complex projects, when we have thousands of rows and hundreds of columns to process, tools alternative to Excel can be handy, where we simply need to write a few lines of a script so that we don't need to manually find the different functions and different index in Excel sheet. Well, to move on, I'm going to show that R and RStudio can do much more beyond just data manipulation. In this class, in the future, we are going to learn a few different techniques with Excel to do data analysis. In our syllabus, we have it here. We are going to learn descriptive statistic, some summary tables and data visualization, and basic statistics and probability theory, and sampling techniques. And we also have inferential analytics, as well as linear regression and time series analysis. These can all be done in R fairly easily. For descriptive statistic, for example, we can find the correlation coefficient between two variables using the correlation function. Here, I'm saying that the two columns I want to find the correlation is between the column that's inside the car data named sales February 2018 by designating using the $, and another variable would be 2019 sale. So let's see that this correlation coefficient is 0.935. This is very high. We can, of course, using the width function so that we don't have to type the car data time once and again. It gives the same result. So here, basically, we are saying that within this data frame car data, we find the columns named these things. So we no longer need to specify the column, the data frame name for each column. And R can be very helpful when we want to do automatic reporting. So here I wrote a very simple for loop so that it loops over unique manufacturers and find the data for this manufacturer and prints an outcome, which is the sum of sales, whether it's increased or decreased. Let's see the result. So here, in no time, it looks through the, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different manufacturers. And based on the sales summary statistic, the sum of sales decreased or increased. It seems most of the sales decreased and only 2 increased. So this is how you can do a for loop. I won't go into the details, but as you can see, it conveniently gives us some automatic reporting so that you don't have to write each line yourself. Using R, we can also do hypothesis testing easily. For example, to test whether the correlation coefficient between the 2018 sale and 2019 sales is significantly different from 0, we can use this correlation test function as correlation test. And here, simply we find the test statistic, some df, a p-value, which we will learn in latter part of the course using Excel. A p-value usually smaller than 0.05 is designated a significant result. So here we can announce that we have evidence showing statistical difference from the correlation coefficient, which we observe as 0.93, actually 0.94, rounded, from 0. Well, some students would ask, typically in previous course, if we already observed the correlation coefficient to be 0.94, why do we have to test it, whether it's different from 0? Well, it has something to do with sampling error. What we observe in the sample can be by chance. If we if we collect another sample, the correlation coefficient can be a different value. So how can we determine whether we have confidence our correlation coefficient is not 0? That's how we can do so by using hypothesis testing, which corresponds with some p-value and some test statistic. Here is a t-test. Well, we can also do a t-test for group difference. This is group comparison of the average sales in 2018 and 2019. So here what we are testing is whether the sales in 2018 and 2019 are statistically different. So as we see that we have 2 columns here, we can find the mean value of each of them. As shown here, the mean sales in 2018 is this much, and in 2019 is this much. It's slightly decreased, but whether this slight decrease is statistically significant, that's what we need to test. And here from the outcome, we can see that the t-statistic is fairly small, whereas the p-value is close to 1. It's larger than 0.05, so that we do not have significant evidence showing a statistical difference between the 2018 sales and 2019 sales mean outcome. Well, because here for each of the observation, this 2019 value is matched with 2018 value, we can find a more powerful test that's paired t-test, which essentially tests the difference between paired observations. So here, what we test is whether this difference between 2019 and 2018 is statistically different from 0. Well, the test outcome comes with these. It's a one sample t-test. The sample estimate is this much, negative 812, which shows a slight decrease from 2018 to 2019. So is this difference significant? And from here we find that because the p-value is greater than 0.05, so at some significance level, we do not have significant evidence showing that this decrease or change in sales for matched manufacturers from 2018 to 2019 is different from 0. So we could also say that sales in 2018 and 2019 did not find a significant change. Well, you can also use R to do linear regression, which can be also done in Excel. But in R, we can simply make it in one line. For example, if we want to estimate the sales in 2019 based on sales in 2018, we simply use a linear regression, linear model. In the parentheses, we give a formula where left to the tilde symbol is the y variable, the outcome. Right to this tilde is the x variable, the explanatory variable. Then we designate the data source as the hard data frame. Then Control Enter. It gives us the coefficient estimates. So we can assign this linear model outcome into an object named the OLS model, because this linear regression is typically estimated using a method called ordinary least squares. So that's why we usually call it an OLS estimate. So out of this model object, we can extract the coefficient, right? The intercept and the coefficient. As well as the coefficient can be also done this way, same result. We can also extract the residues, which is the observed value minus the estimated value. And we can also extract the fitted value. We can also find some more details of the model using the summary function of the model object. Here, in addition to the coefficient estimates, we can also find its standard error and t-value and p-value, along with the model summary statistic, which we will learn in the latter part of the course about degree of freedoms and residue standard error, and also R-square. Two types, there's R-square and there's also adjusted R-square. Here it's above 0.8, and we also have F statistic. You will also find these reported in linear regression models when doing it in Excel. You can also view the model to find more components in the model, including residues and coefficients, as well as other components. For example, if we see the components part of the summary model object Then we find this table, which includes not only the coefficient estimate, but also the standard error, t-value, and the p-value, which is this part in the summary output. And we can also find the sigma, which is this much. That's the residual standard error. That's the average distance from the estimated y value to the observed y value. So what we estimate and actually measured the 2019 sales can be assessed by the difference between them. So that's what residual standard error represents, the average distance. And we can also extract the r-squared and adjusted r-squared, which is very similar to these numbers, which is but just not rounded. And we can also test whether some single coefficient is significantly different from a constant. Here I'm testing whether the coefficient of the sales 2018 is statistically different from 0. And because the p-value is smaller than 0.05, so at the significance level of 0.05, we will learn the detail of such hypothesis testing in the latter part of the course in Excel. Because of this, we would conclude that there's statistical difference from our coefficient estimated here, which is 0.82, is statistically different from 1. Of course, we can also test whether it's statistically different from 0. As you can see, the p-value is even smaller, so we may have a stronger evidence to claim such difference. Well, what I love most about R is the plotting function, because otherwise in Excel, I would have to find the regions of cell values to plot and maneuver over the plotting function, plotting window, which to use as the axis, y-axis, and which to use as x-axis, then adjust the appearance, then adjust the size. For doing one plot is okay, but if I do hundreds of plots, which actually happen, then it's not very scalable. But in R, this procedure can be automated by repeating the same functions. So we just load a package called ggplot2 for plotting. Then for plotting, we simply need to form the data into a long format. The long format basically means that for each observation, we can actually see that for each observation, all right, that's fine. There's only one x variable and one y variable. So here I'm going to use year as x and sales as y. So let's just see a basic box plot. It looks like this. Nothing fancy, but it tells us some summary statistic about sales in 2018 and sales in 2019. Here, a box plot, which we will learn in upcoming classes in Excel. The box plot will show the median value using this middle horizontal line, and the first quartile or the 25th percentile using the bottom border of the box, and the third quartile or 75th percentile using the upper, the top of the box. Then these two longer lines is basically 1.5 of this distance, and these dots are the actual observations of different sales in 2018 and 2019. So we can also generate density plot similarly. A density plot is very similar to a histogram, as we can see here. Density plot, when there's more sales in this area, in this range of sales, then the Y value goes higher. We will learn more about what density means in the variable and the distribution section of the course, and illustrate the results in Excel. We can also make some histograms. Here I overlap the histogram of sales in 18 and 19. Red for 18, blue for, or green for 19. And it shows how many different models are manufactured in this range of sales. And last part is a basic scatter plot. So we can make a scatter plot of the relationship between 2018 sales and 2019 sales. We can make these plots more beautiful by supplying more specifications of the plotting function. So here I just generated what I used in the cover photo of this session. So as you can see, this is still a box plot, but I have connecting lines between the matched observations. So we know that for some model, whether the sales increased or decreased from 2018 and 2019. And I also applied some formatting functions so that the sales is shown in thousands, and the year is just as year instead of sales in the year. So it's quite apparent and very simple and aesthetically appealing. Then after creating these plots, we can save that. A typical format is the raster image, PNG. So we can do so by this, and I specify the width and height that's recommended as the number of pixels for Facebook events. And so that's how I generated the exact outcome as here. And because in the beginning, we designated the working directory as the download folder, so that this generated plot is also here, the same folder as we find the original Excel file. So that's the image I generated. This is a raster image. What I prefer is a vector file, which will stay sharp wherever you import it. So here, I use SVG file format for a vector image. As you can see here, that's the vector file. So if you zoom in, no matter how large it goes, the outcome is still very sharp. Instead, going back to this raster image, if you zoom in, as you can see, some part of the text and image elements is already blurred. So if you need a high quality printing file, go with vector, and it also saves file space in most cases. And we can also make a beautiful scatter plot. I wrote many lines, so I won't go through all of them, but just to show you, just to show you the outcome. Please stick a line somewhere here. Well, I'm going to remove this part. All right, as you can see, this is a typical, actually a more a scatter plot with richer outcome. We can create similar plot in Excel, but if you need to repeatedly create similar files in the future, then R could save the time. Once we save it into a vector file, we find that great. Here in the download folder, I have this one. I specifically make sure that this y-axis and x-axis is 1-to-1 ratio, and I added this diagonal line to show the no change line, because if we have sales of 2018 equal to 2019, that's what this diagonal line shows. That means sales in 2018 equals sales in 2019. There's no change. But for points that's below this line, that means the 2018 sale is greater than the corresponding 2019 sale, so it's decreased. But if it's above this line, that means the sales in 2019 is greater than the sale in 2018. So that means the sale increased. And I applied the conditional formatting for the color of the points so that those decreasing models would be colored red and those increased would be colored green. And I also added this trend line, which is the regression line that I illustrated earlier using a linear regression model with the OLS estimating method. And the gray ribbon is the confidence interval for the regression line. We will learn more about confidence interval in the hypothesis testing section of this course. All right, this summarizes all my demonstration in R. I hope this gives you a perspective of a different tool that can do equivalent jobs with Excel, and also extend the analysis to richer outcomes and results. But for this course, R is totally out of scope, so no worries, you don't have to learn everything right now, but R might be a further step you want to take after this course. In the rest of the course, we are going to learn most of the content using Excel file. So make sure you review the content that I demonstrate today, or the basic formatting and mathematical operations in Excel. That concludes my demonstration session. I'm going to save my data files. All right.